Hello, space fans. Welcome to another installment. You might have noticed I've got a little change in my backdrop here. I decided to throw up a bunch of the patches and coins of various organizations and programs that I've worked with over the last couple of years while doing this SDA stuff. So hopefully something a bit better to look at than a blank wall. Today's video is going to be on propagation. So there are numerous ways to propagate a satellite's position. We'll start with why do we want to propagate? So if all satellites and spacecraft just streamed their real-time positions to us constantly and we knew where everything was, then we wouldn't need to propagate. But unfortunately, that's not the case. There's no similar thing to TCAS and what aircraft use, for example, continuously broadcasting their location. So, therefore, we get periodically spacecraft positions either from downlink telemetry or optical observations from telescopes of where they are, or they fly through radars, or we pick up their communications and trilaterate their position by picking it up at multiple ground stations. So, there is some way to get an initial position for a spacecraft, but from there, we need to propagate the satellite's position. So, once we've lost that signal or it's moved out of the sensor range of the radar, for example, we need to be able to predict where it's going to be. Thankfully, we've got orbital mechanics on our side, which makes that a lot easier. It's hard for spacecraft to take turns like a car would, for example, or an aircraft with continually changing its direction. So, thankfully, spacecraft are in orbits and we can predict where they're going to be in the future if we knew where they were in the past. So propagation takes the last known position and velocity and then estimates the future position and velocity using various algorithms. What a state vector looks like is, I've shown it just down here below. It'll be a position vector in X, Y, Z coordinates, usually in meters, so SI units. And velocity is the same. It's the velocity in the X direction, the Y direction, and the Z direction in meters per second. So that forms what's called a state vector or a state. And we can propagate that state using a number of different tools. What I wanted to do is go through a few of them here, taking SGP4 as the gold standard. So it's definitely not. SGP4 is a simplified propagation perturbation model to propagate satellite states. There's a number of ways that we can propagate a satellite's position that's even worse than SGP4. So I wanted to go over those kind of dark mode propagators first, and cover off why they could be useful in some circumstances and why they're not the best for or the real gold standard for calculating satellite positions. So the first one in this list, as you can see there, it's a skull and crossbones. It's calculating the Keplerian elements of a satellite. So I assume you know what that means, but look up Kepler's laws. There's 6 orbital elements that define an orbit shape. Things like eccentricity, how football shaped is it, its inclination off the equator, the semi-major axis, which is analogous to altitude. So there's 6 of these orbital elements. I encourage you to look them up and see what they are. But if you have these, you can create an orbit. You can propagate the satellite's position in that orbit using a two-body propagator. Some people get tempted to take those Keplerian elements and hand jam them into what's called a two-line element set, a TLE set. So a TLE set's a special kind of definition for an orbit generated by the 18th Space Defense Squadron, 18 SDS, and it uses SGP4 to propagate the satellite's position. Now, it has the 6 orbital elements embedded into that TLE. So people are tempted sometimes to take the Keplerian elements and just hand jam them into the TLE. And that's wrong for a number of reasons, but it does give you an orbit that you can propagate using the TLE. The reason it's wrong is because the TLEs are generated using the mean orbital elements, which is the average orbital elements, not the instantaneous ones that you would be hand jamming into this TLE. So that's why it's got a skull and crossbone on it. It's the worst way to create an orbit for a satellite. But you'll be tempted to do it when you're first starting out in this industry. And I encourage you to do it so you can see, what it gives you. And I'm going to compare these variety of different propagators in space copy for you in a minute. The next type is taking a state vector, so that position and velocity, converting it to Keplerian elements, and then propagating that using a two-body propagator like Vallejo, for example. This will basically, the two-body propagator only accounts for the gravity of the Earth using a simplified model, and it assumes a point mass for the satellite. So it's a very basic propagator, doesn't account for the oblateness of the Earth, aerodynamic drag, solar radiation pressure, or anything else. So that's why it gets a 1 star. 2 stars as we're getting a few more considerations in our perturbation model. Perturbation just means things that would affect the orbit, by the way. So the 2 star is a state vector. This time we're going to propagate it using an analytical propagator. In Space Cockpit, we've got an analytical propagator that accounts for the J2 and J3 spherical harmonics using Vinti theory. So that just means it's accounting for the oblateness of the Earth in that state vector propagation. 2.5 stars. So you can actually generate a TLE the proper way rather than trying to hand jam in the orbital elements to build your own TLE. You can actually do a Newton method fit to the TLE. So you take an initial guess, and then basically you tune the parameters of the TLE and you propagate out the orbit until you get something that is close to your state vector that you feed to the system. So this is kind of nice. We have this in our Wayfinder orbit determination tool, which I'll provide the links in the bottom below. But you can actually perform a state vector to TLE conversion, and it will do that iteratively step towards a solution, and output of that will be a TLE that you can put into various visualization tools like Space Cockpit. The 3-star version, we finally got to it, is the TLE that's generated by 18th Space or 18th SDS now, and it is what is propagated using SGP4. As you can see in the right-hand column here, I've got kind of use cases for these various things. So TLEs generated by 18 space and propagated using SGP4, they're good for general SDA analysis. The error on a TLE is about 1 kilometer, and that grows at about 1 kilometer per day. So that's still good enough when you're considering things at GEO, which are hundreds of kilometers apart, for example. It's okay to get a general idea of where things are in LEO, but at LEO, generally, we have missed distances that are less than 1 kilometer. So it's not sufficient for doing things like conjunction assessment or rendezvous, docking, and that sort of thing. But it's good for just general space domain awareness. Going back up the chain, these kind of skull and crossbones and 1 star, they're really only good for doing sensor tasking, rough sensor tasking. So you can basically tell a ground station provider, hey, there's a satellite, it's coming overhead, it should be within this time window. And you're going to be off, but hopefully the pass is long enough that the error doesn't affect them actually being able to get a collect. So up here I said a couple of orbit periods out. After 3 or 4 orbit periods, your true anomaly where you are in the orbit, that's going to have drifted enough that it's going to be getting hard to get a sensor pass. Depending on all of the look angles and everything, passes typically only last between 4 to 8 minutes. So you're only good for a couple of orbit periods here on these 1 stars. With the state vector propagated using the analytical propagator, you should be able to propagate out a couple of days and still be good enough for sensor tasking. And with TLEs, definitely a couple of days, up to 7 days, you can propagate those and still get accurate sensor tasking schedules. So everything below is what I'm going to demonstrate next, but you can see there's a 4-star and a 5-star here that I've put as well. So 18th Space actually produced what's called a 3-line element set, and it's propagated using SGP4XP. And it gets accuracies that are getting close to numerical propagators. So that's the next thing coming down the line. So that is getting good enough for conjunction assessment at GEO, maybe not at LEO, but it's getting close. And then the 5-star, kind of, the platinum level propagation is numerical integration. So basically we step at every time step, we recalculate the position and velocities of everything. and then we step to the next time step. It's very slow, computationally heavy, but it's the most accurate, and you can basically bolt on different perturbation models onto that propagator to make it more and more accurate as you get more information. Examples would be atmospheric drag, solar radiation pressure, the gravitational effects of the moon, Jupiter, Saturn, and all the other planets at a particular time step. There's a number of different things, general relativity as well. All of these things add to the perturbations, and we can accommodate for them in this numerically integrated special perturbations propagation. So this is really the diamond standard that people use for doing things like conjunction assessment in LEO, where if two satellites are traveling at 7 kilometers per second, if you're off by a second, that could be 14 kilometers error. So you want to be doing time steps at 1/10,000th of a second, for example. As you can see, it's going to be very computationally heavy to do that. The good thing about SGP4 is it kind of trades off trades off accuracy for speed. So the S in SGP4 stands for simplified. So it takes a simplified model of the Earth's oblateness. It does account for some three-body effects, such as the moon, but only above certain altitudes. It uses a Taylor series for integration, so that error grows over time, and that's why we get that 1 kilometer error per day. But yeah, I encourage you to go in and read more about SGP4 if you're interested in it, but it is just a nice basic place to start. A couple of traps for young players. So TLEs assume a coordinate reference frame called Temi, and that accounts for the Earth's nutation and precession. In the community, we kind of generate state vectors in a ECI J2000 coordinate reference frame is our community standard. So if you are generating state vectors from a TLE, then you need to do a conversion back to J2000. And back the other way, if you're taking a state vector from J2000, you need to convert it to TEAM first before applying it for SGP4 models. The SGP4 model uses the WGS72 standard for gravity. So that's a study that looked at the lumpiness of the Earth and the lumpiness in the gravitational field. There are newer models now, such as WGS84, but the SGP4 propagation standard doesn't use them. So if you want to be consistent with the community, you shouldn't be using WGS84, you should be using WGS72. Just hang on and wait for SGP4 XP if you're wanting to do more accurate propagations later down the line. All right, so now I'm going to show you some of these propagation methods side by side. As I said, we want to start at SGP4 and go back to look at some of these bad propagators because they are useful for doing different things. Sometimes you just have to create an orbit and propagate it out a bit because all you know is the inclination, semi-major axis, eccentricity, and basically a launch time or something for creating launch nominals. So these propagators are useful in particular circumstances, and they kind of get glossed over, and people kind of write them off. And everyone goes for the numerically integrated diamond star solution. But I wanted to show that there are other propagators out there that are even worse than SGP4 but are useful. So the first one, we generated a TLE just from Keplerian elements. So I took the inclination and all the Keplerian elements, and I literally hand jammed them into a TLE. Completely wrong, but we're going to see what it does, what orbit it generates. Then I took a state vector of the ISS. I propagated it back to its epoch, took that state vector, and I propagated that state vector using the analytical propagator. I then also used the crappy TLE we generated up here from Keplerian elements, and I fed that into our state to TLE fitter. So this is a function that is in Wayfinder, which is a tool offered by Sabre for doing various astrodynamics functions via an API. So it takes a time step and it fits a TLE to a particular state and tries to minimize the error between the two. And the output of that is a TLE. So we'll show you how that looks. And then we've got the baseline that we based all this off, which was an 18th space, bona fide, verified TLE generated by 18th. So now we're going to compare and contrast how they actually look and how they propagate out. Okay, here we are in Space Cockpit, and you can see I've got a number of satellites here in the scene. The first is this ISS. So this is our 18th space TLE of the International Space Station, and it was epoched here at 26th of November at 1339 seconds. So what I've done is created the hand-jammed Keplerian elements. I've obtained the state of the ISS by clicking the state tab. This will give you the state vector at that particular time. So at epoch, this is the state, and I've then propagated that state using the analytical propagator. Then I've also fed that state, same state, to the state to TLE fitter in Wayfinder and used that to generate a TLE. And then I've imported that TLE into Space Cockpit. So first of all, just to show you how you can do all of this, to create a satellite, for example, if you want to base it off Keplerian elements, you can punch in the Keplerian elements here, and this will create you a skull and crossbones orbit. It'll hand jam a TLE for you, Keplerian elements. You can also create a satellite from a TLE just by pasting in the two-line element set here. You can create a satellite based on a state vector, and this will take a state and propagate it using the analytical propagator. You can also see another option here called cislunar orbit. That's something that we're working on at the moment. That will actually take a cislunar orbit from the JPL 3-body propagation library and propagate it for doing cislunar scenarios. So that's how I created these orbits. I'll also show you Wayfinder here. So if you go to od.spacecockpit.space, you'll see there's a number of functions here. One of them is called a post TLE fitter. Oh, sorry, post state to TLE is the one you're looking for. So example in Postman is given here. So basically you just punch in the state vector, position and velocity. You give it an initial guess. Now I used the bad orbit as the initial guess. So the skull and crossbones TLE I used as the initial guess. I gave it a 0 B star and 0 mean motion first and second derivative just to see what it would do. But if you know the B star, so if you know the ballistic coefficient of the object and you know the first and second derivatives of mean motion, you can improve the TLE that this will generate by including those. If you don't know them, just keep them as 0. It means your propagation won't be accounting for those things in the propagation. But if you don't have that information, you don't have the information. So now that we've imported these into the scene, let's zoom in. And we can already see the Keplerian is off in inclination here. Next off is the fitted TLE. And the SGP4 TLE and the state vector are right on top of each other. Now, that's not too surprising because the analytical propagator is literally just taking that state and then propagating it out using the analytical model. So the initial state is going to be spot on for this guy, whereas the TLE fitter actually fit a TLE to the state. So there's going to be some initial error, but over time it should be more accurate. So if we propagate this out now, zoom out a bit so we can see the Keplerian. Actually, how about we jump a orbit period? So that's a nice thing. In Space Cockpit, you can jump to the next nodal crossing, the next half orbit period, or full orbit period. So we'll jump a couple of orbit periods here. We can start to see how these separate out. So now our analytical propagator is 31 kilometers off. Our fitted TLE is still nice and close. As we propagate this out a number of days, you can see our fitted TLE is pretty good. And the analytical propagator, its error is slowly growing. And the Keplerian is growing much quicker. But you can see, they're all in plane. Their true anomalies are off, the Keplerian in particular, so that's going to affect our ability to do sensor tasking, but only by a couple of minutes. You can see we've propagated out about a day now. So after about a day, the Keplerian one, we're doing about 15 orbits a day. So it's off by a significant amount, about 1,000 kilometers in true anomaly. The analytical and fitted TLE are still well within sensor tasking range, after a couple of days there. So yeah, I encourage you to play around with this. I'll include a scene file where you can import these orbits and play with this yourself in Space Cockpit. As I said, you probably want to be using TLEs, and then on top of that, using numerically integrated propagation of state vectors. but we don't always have this information available. So it's good to know that there are these other methods for being able to determine spacecraft position and propagate that out. So that's all I got for you today. Happy hunting, and yeah, take care.